welcome to another online course. So, in the previous module we have looked at SSB, that is single sideband generation using frequency discrimination. In this module let us start looking at a different technique for SSB generation, that is generation of single sideband modulated signals using phase shifting technique or phase shifting method. Okay. So, this is the phase shift method. So, what we want to look at, we want to look at SSB generation. We have already looked at SSB generation using frequency shifting, SSB generation, and let me remind you once again, SSB stands for single sideband SSB stands for single sideband modulation, and we are going to look at SSB generation using employing the phase shift. So, what we want to look at is the phase shift method for the generation of single sideband modulated signals, and to understand this better we have to start with the Hilbert transform. So, we want to understand the phase shift method. Let us start by first learning about another important transform technique, that is the Hilbert. Unlike the Fourier transform, the Hilbert transform is a time domain transform, that is it transforms one signal, that is Hilbert transform is a time domain transform in the sense it transforms one time domain signal into another time domain signal. So, the Hilbert transform of a signal is another signal, alright. So, what is the Hilbert transform? The Hilbert transform is basically, let us say, let me describe it at a high level, MT pass through this system which is termed as the Hilbert transform or the Hilbert transformer, pass through a Hilbert transformer gives your signal m hat of t and m hat of t. So, this is the your message, this is the message signal or the original signal pass through a Hilbert transformer which is a LTI system. This is an LTI system. We are going to see how to characterize this later. Pass through an LTI system, and this is m hat of t, which is the Hilbert transform of MT. Okay. So, m hat of t Hilbert transform of MT, m hat of t, the Hilbert transform of MT, and this Hilbert transformer, you remember we said the Hilbert transformer is an LTI system, that is it is a linear time invariant system. Therefore, it is characterized by an impulse response, alright. Every linear time invariant system is characterized by an impulse response. Let us term this response as HT of t. This is your impulse response of the Hilbert transform or the Hilbert transformer. Of the Hilbert transform. I am going to abbreviate this Hilbert transform as HT. Now, let the Fourier transform of this Hilbert transform. So, please pay attention because there are several quantities here. Let us denote that by HT of f, that is the Fourier transform of the impulse response HT. Fourier transform of the impulse response HT HHT of the HHTT of the Hilbert transform. Let me write this. This is your Hilbert transform, which we are abbreviating using the acronym HT. So, what we are saying is we need to understand this Hilbert transform. Hilbert transformer can be characterized as an LTI system, all right, and with impulse response H subscript HT of t, all right, where t denotes the time, and with corresponding Fourier transform of HHT t given as H capital H HT of f, that is a spectrum of the Hilbert transform. Okay. Now, it is easier to characterize the, and therefore, what we have is, before we proceed further, the Hilbert transform m hat of t of mt is nothing but the output of mt to the Hilbert transformer, which is basically the convolution of. So, this is the relation, convolution of the original signal mt with the impulse response of the Hilbert transformer. So, this is your convolution . This is the convolution, this is your Hilbert transform of mt, mt is the message signal, HHT is the impulse response of the Hilbert transform. So, m hat of t is basically the convolution of mt with the impulse response of the Hilbert transformer, that is HHT of t. Now, what we want to do is to characterize the Hilbert transform, we want to find an expression for the impulse response. For the impulse response H hat of t of the Hilbert transform. However, the Hilbert transform is more readily expressed in the frequency domain. It is easier to understand its characterization, in the, that is, it is easier to characterize the spectrum, it has an elegant characterization, the spectrum of the Hilbert transform, that is HHT of f. However, it is easier to characterize HHT of f. So, we will start with that. However, that is the spectrum of the Hilbert transform. You can also call this as the spectrum of the Hilbert transform. And indeed, the spectrum of the Hilbert transform, it has an elegant representation that is given as HHT of f is minus j sine of f. I am going to explain what this sine function is shortly, where this sine function this is sine of f is literally the sine function which is 1 for all positive f, that is f greater than 0, 0 for f equal to 0, minus 1 for f less than 0. So, the sine function, sine of f is basically the sine of a number. So, it is 1 for every positive f, that is when f is greater than 0, minus 1 for negative f, that is when f is less than 0, and at f equal to 0 it is equal to 0. And the Hilbert transform HHT of f, the spectrum of the Hilbert transform rather, is basically minus j sine f, which means, now using the definition of sine f above, the sine function of f HHT of f equals minus j for f greater than 0, minus j for f greater than 0, 0 for f equal to 0, and j for f less than 0. This is an equivalent expression of the spectrum of the Hilbert transform. And therefore, now if you look at the sine function, the sine function looks something like this. So, let us first draw the sine function. Sine function is 1 for f greater than 0. So, this is in the frequency domain, this is 1 for f greater than 0, at 0 it is equal to 0, and for f less than 0 it is minus 1. So, this is basically your sine function. So, this is your sine function, this is sine of f. Okay. Now, therefore, now if I multiply this by minus j, that is to obtain minus j sine of f. Now, look at this, this is a complex quantity, this is a complex quantity. So, I cannot readily plot it, this is complex quantity. So, minus j sin f is a complex quantity, it is minus j for f greater than 0, j for f less than 0, and at f equal to 0 it is 0. However, I can plot the magnitude and phase response of this. So, the magnitude of this, the magnitude or of the magnitude response h t of f equals magnitude, you can see this is the magnitude minus j sin f, which is basically the magnitude of minus a j times the magnitude of sin f. Now, magnitude of minus j is basically 1, magnitude of sin f is 1 except f equal to 0, where is 1 for f not equal to 0 and magnitude of sin f equal to 0 for f equal to 0. So, the magnitude response h transpose f is 1 for f not equal to 0, 0 for f equal to 0, and therefore, if I plot the magnitude response, that is if I plot the magnitude. So, since this is a complex quantity, I am plotting the magnitude and phase response of the spectrum of the Hilbert transform. The magnitude or magnitude response is 1 for all frequencies except at 0, ignoring that point, except for that 1.0 where it is 0, it is 1, it is unity. So, the magnitude response looks like this, except at 0 where it is equal to 0, except for this single point, the magnitude of this magnitude of h, the magnitude response of h t of f is 1, and the phase response. Now, if you look at the phase response of the Hilbert transform, that is the phase of minus j sin f, which is minus j for f greater than 0, which means phase of pi by 2 for f greater than 0, 0 for f equal to 0, which means phase of 0 for f equal to 0, j for f less than 0, which implies pi by 2 for f less than 0, and therefore, the phase response, if you can look at the phase response of the Hilbert transform, the phase response of the Hilbert transform, that looks at as follows. For f greater than 0, it is equal to pi by 2, for f less than 0, f greater than 0, it is minus pi by 2, for f less than 0, it is pi by 2, at f equal to 0, it is 0. So, this is basically your phase response. So, basically if you can look at this, you can see that the gain is unity except at f equal to 0, and all positive frequencies are shifted by minus pi by 2 phase, all negative frequencies are shifted by the phase pi by 2. Therefore, this is a phase shifter. Basically, this is what this is doing is this is shifting the Hilbert transform. If you can see, it is shifting the phase, all positive frequencies by minus pi by 2, all negative frequencies, negative frequency components by pi by 2. So, this is basically a phase shifter, alright. So, the Hilbert transform, it has a gain of unity, and the phase for all the positive frequencies, phase shift is minus pi by 2, for all the negative frequencies the phase shift is pi by 2. Okay. So, now simply, although I cannot represent this complex quantity in terms of a 2-dimensional plot, I am going to simply represent this for convenience as I am going to draw this, although strictly speaking this does not make sense. I am going to simply draw this as j. I am going to simply represent this minus j sin f by minus j and j. So, this is basically minus j sin f, although this is a complex quantity. So, strictly speaking this is not correct, but for the sake of convenience we can simply represent this as minus j sin f with 0, that is equal to h t of f, that is minus j for all f less than equal to 0, j for f greater than equal to 0, and this is basically, remember, for convenience, all right. Simply, although it does not make this plot does not make much sense, this is simply for our convenience we are drawing this as j, I am sorry, j for f less than 0 minus j for f greater than 0, all right. This is simply for the sake of our convenience. Okay. Now, what we are going to do is we have characterized the magnitude, we have characterized the Hilbert transform in the frequency domain, that is the spectrum of the Hilbert transformer, which is an LTI system, right. We have characterized the spectrum of the Hilbert transform. Let us now from the spectrum try to construct its impulse response. So, now what we want to do is want to construct the impulse response of the Hilbert transform and to characterize the impulse response of this Hilbert transform, correct, this impulse, remember this impulse response of the Hilbert transform, that is denoted by the Hilbert transform, impulse response of the Hilbert transform which is denoted by h t of t, this is the impulse response of the Hilbert transform. Now, towards this we will use the derivative property of the Fourier transform. To characterize this impulse response, we will use the derivative property of the Fourier transform. The derivative property, now the derivative property of the Fourier transform is as follows. If derivative property is as follows, if consider a signal x t which has Fourier transform given by x of f, that is x t is a signal whose Fourier transform is given by x of f, then the Fourier transform of the signal dxt, that is the derivative of x t is given by j 2 pi of x 2 pi of f times x of f. So, this is the Fourier transform of the derivative of x So, what we have is that if we have a signal x t which has Fourier transform given by x of f, then the Fourier transform of its derivative, that is dxt by dt, is given by j 2 pi f times capital F, that is j 2 pi f times the Fourier transform of x t, that is the Fourier transform of dxt by dt. Alright. So, we will use this property in the next module to derive the impulse response of the Hilbert transform. Alright. So, in this module we have seen, we have introduced the Hilbert transform as an LTI system, that is we pass a signal mt through the Hilbert transform, it gives the Hilbert transform, that is m hat t of mt. We characterized it in the frequency domain, the spectrum of the Hilbert transform as minus j sin f, therefore, it is minus j for f greater than 0, j for f less than 0 and 0 at f equal to 0. We have seen that it is a magnitude response of unity and phase shift of minus pi by 2 for f greater than 0 and pi by 2 for f less than 0, alright. And now we are trying to construct the impulse response of the Hilbert transformer from the frequency response.